so today we're going to talk about thermochemistry as well. Alright, so what do we know about this word? Well, we know that chemistry is reactions and atoms and elements and how all those atoms work, because that's what our whole class is titled. What about thermo? What other words do you know that have thermo in it? Thermometer, that's right. What was that other one? Thermostat. Okay, that's a really good one. What do those things measure?
Heat.
Temperature or heat? Temperature is a measurement of energy and amount of energy. For our purposes. Right? This concept of energy. Energy is a hot topic anymore. We talk about going green and saving energy. Energy, this is a cheesy statement, but energy makes the world go round. What kind of energy do we usually talk about? We talk about fossil fuels, so we definitely talk about gas and diesel. Lots of people are going to electric cars because we use a lot of electricity. People go to electric cars to save those fossil fuels. Now, electricity isn't exactly the chemistry that we're talking about, not really chemical energy. But it is an energy that we talk about. Okay? What about you personally? Like in the here and now? Do you take in some kind of energy? What kind of energy do you take in? Food, right? Okay. So these are things that we think about on a regular basis. This gas and diesel. When you go to the gas pump, how many of you have filled up a gas pump at the gas pump before? All right. Did you ever see that word octane on the pump? It says 83 octane, 87 octane, 93 for the premium, and even more for other kinds. Octane is C8H18. So, wait a minute. We just took something in our everyday life and looked at it. That's a chemical formula. So that's real life stuff. Why on earth does this chemical make your car go? That's what we're going to talk about with thermochemistry. What about diesel? Diesel fuel. Lots of cars, lots of trucks have diesel fuel. Diesel fuel is this. C12H24. Again, that's a chemical. These are chemical formulas that we need to kind of talk about. And then food. Okay, come down here. Food goes through the digestive process and it breaks all down into proteins and carbohydrates, things your body needs. Inevitably, most of it breaks down into sugar or glucose. Glucose is C6H12O6. Again, that's a chemical. Here's a fun fact. Did you know that your body holds more energy than 20 tons of TNT? Like dynamite? How on earth is that possible? Well, kind of still thinking about this concept, let's think a little deeper about glucose, since that's like your body. You eat food and it becomes glucose. What else does your body need? What other chemical does your body need in order to live. Like if you didn't have it right now, we'd have trouble. Oxygen. All right. And then if you take in this stuff, we have to have waste. We're not talking about the solid waste, but what do you breathe out? Carbon dioxide. That is a waste product of our bodies. You might not realize it, but you also breathe out water. Okay? So this is a very basic, taking it down concept, but there's a lot of things that go from sugar to breathing out carbon dioxide. Happens in your mitochondria and your cellular processes. But the basic concept here is this chemical reaction. Another product is also energy. And that is the thermochemistry that we're going to get to with this unit. In fact, in this, there is 2,872 kilojoules of energy per mole. There's a lot of chemistry stuff we just said. 2,872 kilojoules per mole of energy released when your body has glucose. How? Once again, we'll look at glucose is actually this. So when we break it down from the formula to what we actually would see with the atoms, to how the atoms are actually arranged. Now you don't have to draw this part, but I want you to think about it. What are these lines in between the chemical symbols? What do they represent? Bonds, exactly. Okay. These bonds hold energy. Bonds hold energy. That is potential chemical energy. So when these bonds are broken, these bonds form so the sugar bonds have more energy in them than the carbon dioxide and the water bonds. So extra energy is released right there. Give me a thumbs up if that makes sense. Make sense? You don't have to get the math and all that yet, but the idea that when these bonds are broken, these bonds are made and they don't need as much energy to hold them together, so energy is released. Alright. We have two other words, and then I'll give you some time to work on the CK12 stuff. But is energy released with every reaction? No. And so that's where these two words are going to drive us to. First word is exothermic. Now we talked about therm earlier. What about exo? What does exo mean? Leaving or out of. So if we know that therm is energy or heat, and exo is leaving, then exothermic equals energy is released. And we're going to look at some graphs with these words. The first graph looks like this. I have arrows. Energy is always on the y-axis. And then reaction time, or progress, reaction progress is over here on the x-axis. So for an exothermic reaction, our reactants, well, don't we always start with reactants? All the time? Yes, reactants start the reaction. Or over here, are the products going to have a higher energy or a lower energy? If energy is released, the products are going to be lower. So we have this concept. This is the energy that's released. So if energy is released, does that feel hot or feel cold? So fire. It's my lovely fire. So combustion. Neutralization is also exothermic. But we haven't talked about that one yet in class. There are other things that are exothermic, but for our purposes right now, that's good. So what's the other word? If exothermic is the one word, what's the other word? Endothermic. Right. So we know thermic is energy or heat. What is endo? Inside or into. So they're kind of opposites. If exothermic energy is released, endothermic energy is what? Taken in or absorbed. A lot of times you'll read in the word problems, absorbed. Okay. So we will also have a graph for this one. Same elements of the graph. We're going to have reaction time on the x-axis. We're going to have energy on the y-axis. For this one, are the reactants going to have high energy or lower energy? Lower energy. And our products are going to have higher energy. So that means all of this is energy absorbed. Okay. So does that make sense? Give me a thumbs up if that makes sense. Alright. That's kind of all we need to get to today, and I think, yeah.